So, these are the various reactions, and we also saw the rate constants being very high. How are these rate constants measured? It is a very important aspect. There are two major methods by which these high rate constants are measured. If it is 10 power 4 and higher or 10 power 6 and higher, pulse radiolysis is used. Okay. Yeah, 10 power 6, 10 power 8 and higher. Pulse radiolysis is used for extremely fast reactions. If it is not so fast, 10 power 3, 10 power 6 and so on and so forth, something called a stopped flow method is used. We will briefly look at we will look at pulse radiolysis in some detail and stopped flow in a small detail. So, the principle of pulse radiolysis is something like this. It is used to study the kinetics of a species, we will call it A for the purposes of this discussion, and that A in this case will be a biological molecule as far as this course goes, right, with either hydroxyl or the superoxide radical. Okay. For those rate constants we use pulse radiolysis. So, A is the biological molecule and the other molecule happens to be either hydroxyl or superoxide. The reaction cell contains the species or compound of interest, which is A, the biological molecule, in an aqueous solution typically. A pulse is something of a short duration, energy given in a short duration, 10 power minus 6 to 10 power minus 8 seconds of high energy electrons from typically a linear accelerator is provided to the reaction cell. Okay. Linear accelerators are quite common nowadays. You have benchtop linear accelerators and so on and so forth. You no longer need to go to those specialized places to do these experiments. Okay. So, a pulse of high energy electrons from a linear accelerator is provided to the reaction cell. The A derived radicals, so A interacts with hydroxyl or superoxide and it gives you something. So, the A derived radical are monitored over short times, let us say from 10 power minus 9 to about 10 power 1 seconds through absorbance, fluorescence or APR spectroscopy. So, once you know the concentration variation with time, standard way of initial rates and so on and so forth, find out the slope, you are done, right. So, that is how typically rates are found. So, you need a source of high energy electrons in this case. The other concentration, because remember this is a second order reaction, so two concentrations are needed. One is the concentration of A or A derived radicals, the other one is the concentration of the hydroxyl or the superoxide itself, right. So, the other concentration needed to calculate the second order rate constants are measured by using a suitable probe. I think have I opened up the reading assignment? I will, let me open it up right now. Before I forget it, this is courses new, right? Okay. Okay, done. Whenever you get the time, you could read this for knowing how to follow the concentration of either hydroxyl or superoxide, the other one. Okay, I just opened it up to you. So, now let us look at some details. Okay, these are interesting. When the reaction mixture is pulsed with the high energy electrons, what happens in the first 10 power minus 16 seconds? Okay, these are known through various involved studies. 10 power minus 16 seconds. Absorption of energy by water molecules to result in water ions and activated water species, which are represented as this. Water ions are H2O plus, and H2O star is the activated water species. So, that is essentially what happens when water absorbs this high energy. And in 10 power minus 14 to 10 power minus 16, 10 power minus 13 seconds, in that time frame after absorption of energy, homolytic fission of the activated water species happens and reaction of water ions with water molecules happens. This is activated water species, this is the water ions, and H2O is the water molecule. So, H2O star becomes H dot and OH dot. So, you get your hydroxyl radicals here, and of course, H2O plus interacts with H2O to give you H3O plus, and H3O plus is hydronium ion, which is quite common, and you get your hydroxyl radical here. Okay, so, you have generated your hydroxyl radicals, and in 10 power minus 12 to 10 power minus 11 seconds, the electrons generated by the first in the above sequence of reactions, which is this, gets surrounded by cluster of water molecules, and such a species is called hydrated electrons, represented as EAQ minus. You have an electron which is surrounded by water molecules. All this happens. So, you have these two species being formed, and then you have formation of all these ions here, radicals here, free radicals here, and you have hydrated electrons forming. So, you have these three species H dot, OH dot, and EAQ minus. These are three radicals that result from water absorbing the high energy pulse. These are formed in clusters which are micro regions of very high radical concentrations, and such clusters are called spurs term. So, these form there, and of course, they are all radicals. So, they are going to combine with each other. So, radical recombinations in spurs of course occurs to produce hydrogen peroxide, hydrogen, and all this is complete in 10 power minus 8 seconds after the initial high energy pulse is given. Okay. So, these are the various processes that happen. So, remember we have this A, our interest is finding out the rate constant of the biological molecule A interacting with either hydroxyl or superoxide. Okay. So, you would like to have only A and hydroxyl or A and superoxide, right, but we have all these things. So, if the other radical of interest is hydroxyl, then we would like to have most of the remaining as hydroxyl, at least apart from the A. So, before the pulse exposure, the reaction solution is saturated with nitrous oxide N2O. If this, why is this done? Because this EAQ minus hydrated electron can react with nitrous oxide and give you hydroxyl radicals, right. So, you are forming your hydroxyl radicals from EAQ also. H plus you cannot do much, and as long as it does not interfere with your reaction, you are fine. Okay. So, this happens. So, you have in your reaction mixture at times of relevance only A and the hydroxyl radicals, and you can follow the concentrations of both. If the other radical of interest is superoxide, here it becomes a cleaner system. Why? Earlier we saturated it with nitrous oxide to get hydroxyl. Here you saturate it with oxygen and add some sodium formate to it. Why are we doing this? Because this aqueous electron can react with oxygen to give you superoxide. Also this formate, right, can react with the hydrogen radicals also to give you the CO2 dot minus, and this OH dot interacts with this to give you CO2 dot minus, and the CO2 dot minus can interact with oxygen to give you the superoxide radical. So, you have completely converted everything into the superoxide radical, which is quite nice. So, here you ultimately you have only the superoxide and the A radicals, and you can follow them. So, then the additional reading material will tell you how to follow the hydroxyl or the superoxide. There are complications, huge complications there. The paper tells you some aspects of the complications. The A radicals, A derived radicals we follow by fluorescence absorbance or EPR spectroscopy. So, you have the concentrations of both these species varying with time, very short times of course, and then you can find out the kinetics standard method. So, that is the basis here. For the stop flow, I think we can finish this chapter today. Stop flow, the reaction rate constants are smaller. So, what is done is 2 syringes are taken with these reactants, pressed together into a mixer, and immediately analysis is done in the reaction between them. You follow the concentrations of both species by whatever method, okay, the absorbance, fluorescence and so on and so forth, and thereby you can calculate the rate constants. You can take a look at this video to get some idea of stop flow. We will finish with that today.